Well, welcome back, everybody. Didn't lose too many of you guys. All right. Well, hope you had a good week. A couple of things before we begin. I will begin with chapter 3. Knock that out today and jump into chapter 4. Now, the syllabus is incorrect for the first exam. I sent an email to that. Originally, that was the original date, but I updated it. So it is next week, exam number 1. Okay. So it's not today. Normally what I do is I open it on a Friday and give you Friday into Saturday to knock it out. Okay. So also keep track of your assignments. What I tend to do is I will not make something due until I get done with that chapter. And so I will give you 1 or 2 days after I'm done with a particular chapter we talked about. Whatever chapter we talked about, I'll give you some time afterwards. If you see something that is like due today and we haven't covered it, don't send me an email and I'll move it and correct it, okay? The other aspect is this, a lot of the assignments require me to go in there and do a manual grade for some questions, okay? So that will take a little time. So give me a day or so. So you won't see the final grade until I'm done with it. And that's true for some of the labs and some of the activities and on the homework, not the case with respect to the homework. All right. I also mentioned before, I do have the same class on Tuesday and Thursday. I got a 1 o'clock and a 4:15. If this Friday doesn't work out for you or you miss a particular Friday, feel free to come into those other classes. We are in the other ones, we just started chapter 4. So here we're starting chapter 3, but it's because we meet here one day. You know, if we were all meeting twice a day, we'll be on the same, roughly 1 or 2 slides separate. Okay, any questions? Okay, any questions about the program? Everybody knows where to get your assignments, knows where to get your textbook, and you know everything's all set up for you in modules, so you don't have to search for things. Okay, so if there is a question about that, shoot me an email. We'll make sure you know where you gotta go to get the information. Please don't wait till like mid-semester and tell me, I don't know where the textbooks are at. I've had that before, so, okay. All right, well, I'll tell you what, I will start with chapter 3, excuse me. And here, we're gonna be doing some actual conversions. We're going to be converting from English to metric and metric to English, okay? So I did send to you, everyone, a Word document that breaks the metric system down for you to kind of explain it a little bit. Let me pull that up first, okay? Now, this one. So if you've not received it, let me know. I'll make sure you get it. Our 3 items that we measure: mass, volume, and length, okay? Now, if you look at the similarities there in this particular table, you can see that we got mass. 1 kilogram is equal to 1,000 grams, okay? We're going to just stick with the mass. With 1 gram, there are 10 decigrams. Deci, D-C-E-E-C-I, deci meaning similar to how many years in a decade? 10, right? So you got 10 decigrams in 1 gram. There's 100 centigrams in 1 gram. C for century, 100 years in a century. That helps you out, maybe. Okay. There is 1,000 milligrams. M for millennium. There's 1,000 years in the millennium. So in 1 gram, there are 1,000 milligrams, excuse me. And one you probably didn't know, and that is microgram. That's the mu. It looks like a letter U with a little tail up front. That's micro, so that'd be microgram. there are 1 million micrograms in 1 gram. Now, you can apply those prefixes to volume, okay? So volume being liters, capital L. So we got deciliters, centiliters, milliliters, and microliters. And you can also apply those prefixes to length, and the units we use in the metric is meters. So we got decimeters, centimeters, millimeters, and micrometers. Now, every one of these factors are conversion factors that you can utilize. You can utilize them. You can make even, we'll talk about that, how you can combine some of these. But for right now, until you're comfortable with it, you can utilize each one individually. And you can write it one or two ways. For example, I can write the conversion factor of 1 kilogram is equal to 1,000 grams. I can write it with kilograms in the numerator, or I can write it with kilograms in the denominator. Which one I choose to use depends on the question and the units that I need to cancel and get rid of. Okay, so if you set these up properly with the units, you just go through, cancel the units out, and the only thing left to do is just plug in the numbers in the calculator, okay? For example, what do I mean? Well, if we take this question here, it says, how many micrograms are in 0.125 kilograms, okay? And so we write down what we are given, which is 0.125 kilograms. And keeping in mind that what we're looking for is micrograms. That's the units we need to get to eventually, because that's in the question. And I had kilograms to begin with, so I look for a conversion factor that I can use to get rid of kilograms. Well, I know that there's 1,000 kilograms in 1,000 grams in 1 kilogram. And I write it with kilograms in the denominator. Why is that? Because when I do the mathematics, basic algebra, kilograms over kilograms cancel, okay? And so that puts me in the units of grams, which is not the units that I'm searching for. I need to get a microgram, so I got one more factor here that I input. And I know that there are 1 million micrograms in 1 gram. I put grams in the denominator for the next factor because my grams cancel. You can note that by the line, the red line, leaving me with units of micrograms, which is what the question asked for. Now it's up to you as far as plugging in the numbers into the calculator, and you end up with 125 million micrograms in 0.125 kilograms. Now we can set up multiple of these factors up. Now, I know you're tempted to use the ratio system that maybe you were taught in high school, and that works pretty good. Maybe the first, maybe 1 or 2 conversions, but it can, if you don't set that up properly, mess things up. And so when we get to chemical reactions and calculations of chemical reactions, using the system here will 99%, I guarantee you got to set up properly. Okay, right now we're looking at fairly common units, grams, micrograms, centigrams, so on and so forth. But down the road, we'll be talking about 10 grams of carbon dioxide reacts to give me how many grams of, I don't know, crazy example there. And we're going to use these factors, ratios, from that chemical reaction to set it up in this manner, okay? The other thing too, notice that I mentioned up here, you can set your factor up as 1 with a kilogram in the numerator and 1,000 grams in the denominator, or vice versa. Now, you may be tempted to take the inverse of 1,000 and make it in that number. I suggest you just leave the numbers as it is. 1,000, you put it in the numerator or dump it in the denominator. That way there's no error down the road. So just invert the unit, the ratio, okay? Every ratio that we're going to be using can be set up in this manner, whether it be $50 per hour, okay? That's a ratio. We can set it up as 1 hour per $50. We can use that to do calculations, or 100 miles per hour, okay? We can set that up. The same is true with the conversion factors that we give you, which are in the shapes table, and that there's 1 inch is equal to 2.5 centimeters, 1 pound is equal to 454 grams, 1 quart is equal to 946 milliliters. Those conversion factors can be set up one or two ways, depending on the units that you're trying and striving to get. Okay. Just a quick review on your algebra. A squared divided by A. Simply, A squared is the same thing as writing A times A. We can break it down. A's cancel, leaving us with units of A. Okay, so yes, we're going to be doing some algebra, but some basic algebra, nothing complicated. Mathematics, nothing complicated with respect to any type of quantum mechanics, differential equations, no. Add, subtract, multiply, divide. Okay. All right. So if you did not get this table, just let me know, and I'll make sure you get that. I did send it through email. So. Okay, where were we? Let's go back to the chapter. So with respect to the units in the metric system, I just touched on that. We use meters for length, grams for mass, volume is liters, and time for both metric and English is second. There's a corresponding symbol, lowercase m for meter, lowercase g for gram, uppercase for liter, and lowercase s for second. These are the prefixes, which if you look at the table, correspond to the table I sent you, the Word document. We got K for kilo, which is 1,000 times greater. D for deci, 10 times. C for centi, 100 times smaller. M for milli, 1,000 times smaller. And mu, which is for micro, which is 1,000,000 times smaller. Okay, those are the prefixes. These are very similar to what we just talked about. 1 meter, there's 100 centimeters in 1 meter. There are 10 decimeters in a meter, 1,000 meters in a kilometer, and 1,000,000 micrometers, or microns, they might call it, in a 1 meter, and 1,000. Did I say 1,000? I meant 1,000,000. 1,000,000 micrometers in a meter, and 1,000 milliliters in 1 meter. Okay. So that helps you out to with the prefixes. Now we utilize a system called factor label. The book talks about this factor label system. It's also been called a dimensional analysis. It's basically, I call it, keep track of your units. Okay, that's all you're doing here. So what they have a couple of steps, and I would recommend until you're familiar with the system, is to follow a systematic approach to solve these problems. And once you're comfortable, you can adjust it accordingly. We identified the units that we're looking for, what we're trying to find, what we're trying to calculate with respect to the units. And then we identify what we are given from the problem. Okay. And then from what we are given, and we want to get to units of what we're looking for, we start setting up our conversion factors. All right. And setting it up in a manner so the units cancel out to eventually get us to the point with respect to the units of the units that we're looking for. Now the rest is simply up to you. You plug it in the calculator, plug the numbers in there, and you got your answer, keeping track of your significant figures. All right, so for example, how many liters are in 2,389 milliliters? Well, we write down what we're given, okay? And we should write down what we are looking for with respect to units. So way over here, I may write down equals unit-wise liters, because that is what I'm looking for, okay? And that gives me a direction to go to. The same is true when these are chemical reactions. We write down what we're given, and we write down what we're trying to get to with respect to our unit. And so I plug in a conversion factor here because I know that in 1 liter, there are 1,000 milliliters. So I write it with milliliters in the denominator. Why do I do that? Because because I want my milliliters to cancel mathematically, okay? If you inadvertently invert it and say 1,000 milliliters in the numerator divided by liters, look at the units. What do you end up with? Milliliter squared divided by liters, which that doesn't make sense, right? Okay. So here you can see the liters cancel out, milliliters cancel out, leaving us with the units of liters. And now you basically do the math, and you end up with 2.389 liters. Now here, don't forget your significant figures. The conversion factor in this case is a exact number. So that would not be a factor with respect to significant figures in your digits. So the only number is what you're given, which is 2,389, which means I got 4 sig figs. My answer has to have 4 sig figs. Speaking about exact numbers and where'd it go? Okay, let's do this one here. Okay, you'll notice on the 3 factors that I mentioned earlier, as far as what we give you, that converts you from English to metric. Of these 3 factors, okay, the first one, and I repeat, only the first one is considered to be an exact factor. Whoop. And that, is this. The 1 inch per 1 inch is equal to 2.54 centimeters is considered by convention to be an exact number, and therefore would not be a factor with respect to determining the number of sig figs in your answer. Okay, unlike the other 2, where I got 1 pound is equal to 454 grams. The 454 is a measurement, and therefore there's a degree of uncertainty. Therefore, it would be a factor if you use that in your calculations. So if I need to convert from pounds to grams and the number I'm given has 4 sig figs, well, my answer can't have more than 3 sig figs because of the 454. And by analogy, the same is true for 1 quart is equal to 946 milliliters. The 946 and the 454 are not exact numbers and could be a factor, okay, with respect to sig figs. I understand you can go on the internet and you can get a variety of different conversion factors, give you more digits with respect to 1 pound to grams. I recommend not to do that. Why? Because what can happen is that your answer with Canvas may not correspond, and Canvas is not the smartest software in the world. You might be off by 1 number and it will consider it to be wrong. So use these conversion factors, okay? The same is true for atomic weights. When we get to that, use the atomic weights that on the periodic table that we utilize, okay? All right, so go back. All right, another example here is how many kilograms are in 12,300 centimeters. Okay, so we write down what we're given. Over to the far right, I write down what I'm looking for with respect to units, and I'm looking for kilometers. Okay, that is what I'm looking for. So I'm going to set it up for my conversion factor units. So 1, I can get to kilometers. So I see that I got centimeters. So I got to find something. I need something that will cancel my centimeters. Well, I know that in 1 meter, it is equal to 100 centimeters. So that is my first factor there. Okay. And that takes care of my centimeters. But that puts me, if I were to stop the calculation with the first conversion factor, the units that I would be in would be meters. So I need 1 more conversion factor. And I also know from the table that 1 kilometer has 1,000 meters. So I set it up with meters in the denominator because I want to get rid of my meters. So I check my units. all the units cancel accordingly. And now I end up with the units with kilometers, which is what the problem asks for. So I set the problem up correctly. Now it's up to you to plug it in, plug the numbers in and get your value. Note that the two conversion factors are exact numbers, so they will not be a factor with respect to sig figs. 12,300 has 3 sig figs, and so our answer should have no more than 3 sig figs. Okay, let me clear that up so we can see that. Okay. Now notice here, if you've recognized it, we can take those two conversion factors and combine them into one, right? You know, because if I take and, you know, once you're comfortable with setting them up, then, you know, then you can do that. It's not a problem. You can, it's nothing wrong with it. But you notice if I multiply these two factors together, unit-wise, I get a conversion factor, which is kilometers per centimeter, okay? And so that's another conversion. That's a conversion factor you can make. But until such time that you're comfortable with that, keep them separate, okay? Follow them through. Follow the units through. Okay, some other conversion factors in the English, pretty much straightforward. If you know them, 12 inches in the foot, 3 feet in the yard. You know, also that could be 36 feet in a yard, okay? 1760 yards in a mile or 5,280 feet. We know there's 60 seconds in a minute, okay? 60 minutes in an hour, 24 hours in a day. 2 cups in a pint, 2 pints in a quart, 4 quarts in a gallon. Now that part always messed me up. So what I do is I have this thing to remind me. And we got the big G here, which is the gallon, okay? And then notice inside the big G, the gallon, you got 4 Qs, which represent 4 quarts. So there are 4 quarts in a gallon. Now within the Q, there are 2 Ps, which represent pints. There are 2 pints in a quart. And inside the pint, we have 2 Cs, which is not cubic centimeters, but 2 cups, okay? 2 cups in a pint. So there's 2 cups in a pint, 2 pints in a quart, 4 quarts in a gallon. Every one of these here, every one of these factors is a ratio that you can set up. With first one, 2 cups in a pint, I can set it up with cups in the numerator or cups in the denominator, okay? Every single one of these here. That way you can utilize them to set up your conversion. For example, within the English units, you have how many gallons in 44.5 cups. So we write down 44.5 cups. Keep it in mind, we want to get 2 gallons, so we got to put a conversion factor to get the gallons. And let me do this here just to be consistent. Okay, gallons, that's where we're trying to get to. All right, so I know that in 1 pint there are 2 cups. So I set it up to get rid of my cups in the denominator with respect to my conversion factor. That leaves me units of pints at this point, which is not where I need to be because I got to get to gallons. So I put in my other conversion factor where I get rid of the pint, now puts me in the units of quarts, okay? Which again, I'm not there with respect to units, so I need one more factor, and that is 4 quarts in 1 gallon. Now, as I set this up, like I said, once you become comfortable, you can combine these here. So check my units. Notice that my quarts cancel, my pints cancel, and my cups cancel, leaving me with the units of gallons, which is what we are ultimately trying to obtain, okay? And so now the math is on you. So it's 44.5 divided by, it's what, 16? You know, because 2 times 2 times 4. And you get an answer of, oh, let me clear this up. 2.78 gallons. Again, those three conversion factors are exact numbers. Also, I can convert those three conversion factors to one because if I multiply just the conversion factors with each other, I end up with 16 cups in 1 gallon. Do I not? Yeah. So I can make one conversion factor. All right. So next one says, how many inches in 3.5 yards? Okay, so that is what I'm given, 3.5 yards. I want to get to inches unit-wise, and again, to be consistent. I'm over here. Oh, nope. Oh. Come on, Fred. I'm having a hard time spelling today. That is the units that I'm striving to get. Okay, that's where I'm trying to get to. So I know, okay, so I know I want to get rid of yards. And I know that there are 3 feet in a yard, right? That cancels my yards out, leaving me with feet. And I also know that there are 12 inches in a foot. And so setting that up in that manner, now I know this is pretty self-explanatory, but we're striving the technique of getting to through these units here, but keeping in the back of your mind that these units, these conversion factors, will eventually be converted to chemical reactants and chemical products, okay, in the calculations. All right, so both conversion factors are exact numbers, therefore don't play a factor. And that number is 126 inches. Now, I ask you the question, would that be the number that I would present as an answer, 126 inches? Let me see. Exactly. Christina, because no, we couldn't present 126 inches because we are given 3.5 yards to begin with. So our significant figures here are 2. So our answer has to be converted to 2 sig figs. So the 126, now this is where people get a little bit confused here, but we'll just walk it through. Since I need to convert this to 2 sig figs, okay, because I got 3.5, I first go to the 2 sig fig position, which is the number 2 in that 126. I then look at my neighbor, okay? Now, do not look at, if this had like 20 digits here, don't look at the neighbor like number 19, way down to the right. Look at the immediate neighbor, okay? That's it. Who cares what's after the immediate neighbor? We only care about who's the immediate one here, which is 6. So from there, then we use the rounding rules, which is 6 is greater than 5. Therefore, 12 goes converted to 3. Now we don't drop the 6 because if we drop the 6, we change the magnitude. Right now we're in the hundreds. And if you drop the 6, now you go to the 10th, okay? So if it's before the decimal point, those numbers that you're going to truncate, remove, get converted to 0. If it's after the decimal point, you can drop it, okay? So that 6 becomes a 0. You don't drop it, okay? Because you're in the hundreds range. So it becomes 130 inches. And that is the most accurate you can get because you only have 2 sig figs to begin with. So your answer shouldn't have more than 2 sig figs. All right, if you would have dropped the 0, then you would have 13. So again, the magnitude's incorrect. So don't forget about that. When you're converting numbers with the numbers before the decimal point, you got to get rid of them, convert them to 0. Don't drop them, or otherwise you change the magnitude. I mentioned this already before with respect to exact and approximate or a measurement. The first factor, the 1 inch is equal to 2.54, is considered an exact measurement and therefore wouldn't play a factor with respect to sig figs. The other two, the 454, the 946, are approximate measurements and therefore could play a factor. Okay, and keep that in mind because some of the homework problems come up with having to use one of these two factors. And if you look at the number you're given and you use those sig figs, then it's incorrect because the 454 would be a factor with respect to the sig figs. Okay. Now, obviously, these are given to you because they're on the table. They're in the shapes table. For example, we're going to convert to metric to English. And the question here is, how many pounds are in 248 grams? So, similar system. We write down what we're given for 84 grams. Okay. We know from the conversion factor that 1 pound is equal to 454 grams, and therefore our answer would be 0.546 pounds. Don't forget the units. Without the units, that 546 doesn't mean anything. Okay. Check your setup, making sure that things cancel out properly. Notice my grams cancel. And therefore leaving me units with pounds, so it's been set up properly. Okay. Now, question would be, if this number, okay, let me ask you a question. Instead of 248, what if the number was 248.0 grams? What would be my answer? Okay. So, I mean, but what would be my answer? Instead of using 248, you were given 248.0. Get the landscapers out here. They may be picking, you might be picking up their sound. You follow what I'm saying? If I had, instead of that number, let me instead of 248, I'm trying to mark it out. Okay. Okay. 5436. I'm getting a lot of answers here. 2 runs to 2. Okay. So hold on 1 second. Let me 248. For some reason my calculator is going crazy. Okay, let me do this. All right, well, let's do this. I'll share my calculator. So instead of 248, you're given 248.0, okay? And you divide that by 454, okay? And you get this big old number here. And I'm gonna bear with me for a second, and I will plug that big number in there. That's what my calculator gives me. Okay, let me see. Okay. Now, keeping in mind what I just mentioned about, okay, let's make sure we are all in the same boat here, okay? Instead of 248, you're given 248.0, okay? So it's the same problem. The only difference is you're given 248.0 versus 248, okay? And if you plug into the calculator, you get this big, humongous number. Well, the question is, what is your answer? How do you report your answer? Would your answer be different, or would it be the same? Keep it in mind of what I just stated about those conversion factors that are exact and those conversion factors that are not exact. We have 4 sig figs, okay? Unfortunately, Kathleen is correct. Who's okay? How many? Round up to 3. All right. All right. Let's go back. I'm going to give you some more information, and then you think about it. Okay. I stated earlier that this number there is not an exact number. It's an approximate number. It's a measurement, and therefore would be a factor with respect to sig figs. Okay, so how many sig figs does 454 have? 3. And how many sig figs does 248.3 248.0 have? 4. So how many sig figs should our answer have? 3, which is the same 0.546. Okay. And so at first we look at 248.0 and we think, okay, we got 4 sig figs, our number should have no more than 4 sig figs, which normally would be correct if your conversion factor was an exact number. Okay, so remember that those 2 conversion factors, which I'll go back to. Let me clear my thing here. Those 2 conversion factors right here these 2 right here that are highlighted in red box are approximate. They're measurements, and therefore could be a factor like the example I gave you with respect to sig figs. If you're using the 254, it's exact. It would not be a factor. Okay, so don't forget that. Kind of tricky, but unfortunately, you know, like we stated earlier, that all measurements. Okay, now this one here. Oh, excuse me. The first one is open to argument, and I tend to disagree that this is an exact number because it's a measurement, but by convention, it is treated as an exact number, and so therefore I want to be consistent. So it's an exact number. It's open for argument. I tend to agree that it's not. It's a measurement, but I got to do what the rest of the world is doing with respect to calculations at this point in time. The others are measurements and therefore are approximate. Okay. Any question about that aspect? Because it could be a factor when you do the calculations in some of the homework problems. All right. Oh. All right. Now we got this other example. Let me get this out of the way here. Where they're asking you, how many inches are in 3.54 times 10 to the negative 3 kilometers? All right, so this is where you might get your calculator and get the hang of how to input in scientific notation. And if you're having trouble with that, let me know. And send me an image of your calculator, and we'll try to figure out where your buttons are at. Okay. You have 0.00354 for what? Oh, yes. That would be the correct number. Sarah, I was trying to figure out what you were typing. 3.54 times 10 to the 10 to the negative third. It just moved the decimal point over 3 positions to the right. You can write it longhand, type it in longhand. But, to get used to learning how to use scientific notation, because we will be using scientific notation with big numbers. You may want to practice inputting that number. Okay. All right. So writing down what we have, and I set up a series of conversion factors here because I start off with kilometers. So I got to get rid of kilometers. Okay. And my first one will get rid of kilometers because I know that there are 1,000 meters in 1 kilometer. So at this point, with the first factor, that puts me into the meter range. Now, I want to get rid of that and go into centimeters. Why? Because I know that in 1 inch, there are 2.54 centimeters. So I use another conversion factor to get me into centimeters. So the meters cancel out. And at this point in time, with the second factor, that puts me in units of centimeters. Now, finally, I can use the 2.54 centimeters in 1 inch, set that up with inch in the numerator, okay, because that is the units that I'm looking for, okay? And that is equal to 139 inches, yes. In your calculator, Sarah, you typed in 3.54 EE, that is, the EE is the scientific notation for your calculator. It could be the EXP, and then you type in -3, give you that number in scientific notation. Now, your calculator may put it in longhand or keep it in scientific notation. Depends on the form or the mode that you have the calculator set at. Keep it in mind. Oh, and then finally back to this one here, 2.54. It's an exact number. So all 3 factors are exact numbers, so they will not be a factor with respect to scientific notation, and therefore our answer would have 139 inches as far as the number. Now, these 3 factors, this is a good example of what you could probably end up with when you do the calculations with respect to chemical reactions. You'll find that at the minimum, you're going to have at least 3 conversion factors, 3 ratios to set it up. And so that's why I can't overemphasize practicing this method, because I know you'll be tempted to say, well, I can do this and I can do that. Get used to you doing it this way so that we can use this same technique when we get to chemical reactions. Also, occasionally you have to do a show me type of work. This is the show your work type of scenario. It's showing the conversion factors and how you set that up. Okay, and when I look at them, if I have a problem like this, generally if this problem was worth say 5 points, normally it's 1 point for the answer, and then the rest of the 4 points is the way you set that up, which means that if you typed in the wrong number and you get a wrong answer, you only get 1 point taken off. If you set that up properly, you still get your other point, okay? But if you just give me an answer, which is correct, well, that's only worth 1 point. I can't give you the rest of the points for not showing your work. See how that works? Yeah. All right. There's a question here. Here's there. If the problem asks to show the question, Kathleen has a question. It says, can we move the decimal point? If the problem says show the work, then I would strongly recommend you show your conversion factor. If it doesn't say anything about showing your work, yes, moving your decimal point over 3 positions, that'd be perfectly fine. Okay. All right, did that answer your question, Kathy? Okay. Okay, no problem. All right, so here's a scenario. You know, we do these conversions to metric in English, and it's really kind of crazy because when I was a child 100 years ago, we were trying to convert the U.S. trying to convert to metric, and we still here we are 100 years later, and we're still using both units. You know, because it really amazes me that we go get a gallon of milk, but I get a 2-liter bottle of soda pop. So right, you know, okay, maybe even another 100 years to be completely converted over. So we got 2 liters of soda bottom. We want to figure out how many quarts do we have. Okay, so therefore, we set up the problem with, 2.0 liters. We need to convert that to milliliters because I have a conversion factor that says in 1 quart, there are 946 milliliters. So I set up my problem. Okay, double checking my units, making sure that my units get canceled out properly. Okay, and now the question is the mathematics. And just plug it in your calculator. You should end up with 2.1 quarts. Now, why 2.1 with 2 sig figs? Because the question gave you 2.0, which has 2 sig figs, but bear in mind, the 946 is a measurement, but it has 3 sig figs, okay? 3 sig figs. All right. So that wouldn't be a factor this time. But if that was like 2.000, then the 946 would determine how many sig figs you had, right? Okay. All right, so practice the conversion factors, you know, use the conversion factors that we give you because it could give you some other numbers that when you plug them into Canvas won't recognize it and count it wrong. And I don't want to count you wrong. All right, so if you have any questions about these, you know, after you work the problems, feel free to shoot me an email. We can talk it through. We're going to briefly talk about this volume by displacement. Okay. We all know what we're familiar with this. Really, you jump in the bathtub. What happens to that level of water? It goes up. And so if you have or a jacuzzi, so if you can measure that volume of water beforehand, you know how many gallons, for example, or milliliters or liters of liquid are in there, and you jump in, and then you are going to displace that volume, which means that the volume goes up, okay? And if you had a means to measure that difference of the final volume minus the volume you started off with is the volume that you displaced, okay? And that is your volume. And so we can utilize that because down the road, we can calculate what's called density, which is a ratio of mass over volume, okay? So for items that are kind of not regular, because if it's a rectangular or square or something we can measure, that's straightforward. We can measure that length, width, and height, we got it. But there's numerous things that we can't do that because of the shape. So we use this technique of displacement. So in this scenario, remember that 1 milliliter is equal to 1 cc or cubic centimeter. A diamond is put in a graduated cylinder. It's just a cylinder with markings that tell you the volume. It initially starts off with 20 milliliters of water. Then you put the diamond inside, and it just happens to be a diamond. It could be anything. And then the volume goes up by displacement, and it goes up to 34.7. And so that difference of volume is the volume of the diamond, okay? the new volume 34.7, no, that is not the volume of the diamond. That is the volume the diamond displaced, brought it up to. Okay, so you got to take the difference where it ended up and from where it started. So that diamond has a volume of 14.7 milliliters. Okay. All right. Now, if we do a calculation of a box, a rectangular box, it's pretty straightforward. It's simply length, width, and height. And we can calculate the volume of this box here is 24 centimeters by 11 centimeters by 16 centimeters. Okay. Plug in the numbers, calculate them. Keep it in mind the units. Okay. Because in multiplying units, centimeters times centimeters is centimeters square, times centimeter is centimeters cube. And if we multiply again by centimeters, it'd be centimeters to the fourth, centimeters to the fifth, et cetera, et cetera, et cetera. Okay. We got 2 sig figs, so your answer should end up with 2 sig figs. All right, so that represents 4,200 cubic centimeters. Can anybody tell me how many milliliters that would be, 4,200 cubic centimeters? (4,200 cubic centimeters). How many milliliters would that be? 4,200, exactly. How many liters would that be? I got 4,200 milliliters. How many liters would that be? Here's a good example. Now you can move the decimal point over very quickly, 3 directions. There you go, 4.2. Exactly, 4.2. Imagine in the car engines now, they give you the volume of the engine, the size of your engine is liters. It used to be back cubic inches back in the day. Everything's volume. So there we go again. Some things are metric, some things are not. All right. Density. This is why we talked about this displacement or volume displacement. Density is another ratio. Keeping in mind the ratios, like I said earlier, every ratio that we're going to use, we can invert and write it the other direction. You use it in calculations. Density is simply the mass divided by the volume. The mass, straightforward, we weigh it. That's our mass. The volume, if it's irregular shape, then we maybe do a displacement experiment to get its volume. Or if it's a regular shape, we can just simply measure it, length, width, and height to give us the volume. Generally, the units for density are grams per milliliter. That's the most common units, but you'll find a combination of all. You find kilogram per liter, grams per cubic centimeter, etc. But the most common unit is grams per milliliter. Okay. All right. So density is just simply, how much matter is in a given space. Now, it's a ratio. I want you to think about this. You all heard the old thing about, okay, what weighs more, a ton of steel or a ton of feathers? Well, obviously, they're both the same. It's a ton of each, kind of a crazy question. Now, I'm going to pose a question to you now. Who has the greater density? A ton of steel or a ton of feathers? What do you think? Remember, I didn't say the weight. I said who has the greater density? Okay, you got 2 steels. Okay. Okay. You got 2 steels so far, 3 steels. All right. All right. The answer would be it depends. Okay, you might say, whoa, wait a minute. What do you mean depends? Now think about this for a moment. We got a ton of steel. All right. The solid, remember the properties of solids? They have a set volume, okay? The atoms are all compressed. We can't compress them anymore. And so that ton of steel could be a block of steel, and we can measure its volume, whatever the volume is, length, width, and height, okay? Now, Feathers, we get a ton of feathers, but its volume can vary. We are, if you have, think about this, if you have a pillow made of feathers, can't you squish them? Okay. There's a little bit of give there where we can put that ton of feathers into a compactor and squish the volume. So we could probably squish that volume enough such that the denominator gets smaller. And that means the density goes up, right? And so it depends if we can crush the volume of those feathers and get it to the point where it has a density greater than steel. Another example for would be a loaf of bread. Okay, you buy a brand new loaf of bread. Okay, and we can measure that length, width, and height. It's got a known volume. We can put it on the balance and weigh it, and guess what? We can calculate a density for that loaf of bread. And then what happens? You take that loaf of bread, same weight, and you crush it. You smash the volume together. You have changed that ratio. You have changed that volume. Okay, you made it smaller, so the density goes up. Okay, that is why ice floats, because ice is nothing but water. The thing is with ice, when it's a liquid, it has 1 gram has a density of 1 milliliter. If I take that same gram and I freeze it, that 1 milliliter expands to about 1.1. So now the density is roughly about 0.9. So that ratio changes. Okay. The ratio, when you have a ratio, you can play either the numerator or denominator to change that density. All right. So it makes sense that the state of matter that is most dense would be solid, because what's happening with the ones with gas, they're so, depending on the container, it can vary. It is such that the density of gases are very, very small. Solids are very, very, very high. Now, the density of water is our reference point. Normally at 25 degrees, the density of water is 1 gram per milliliter or 1 gram per cubic centimeter, which means this. If something has a density greater than 1, if it's in water, it's going to sink. If it has a density less than 1, if it's put in water, guess what? It floats. Okay, so we kind of use that as our reference point. Now we can do density calculations. Now, the way we do this is the first one's very straightforward. We're given a mass, we're given a volume, divide, you got the number. But we can also use the density of a liquid or a material to do some calculations with it. For example, the density of chloroform is approximately 1.48 grams per milliliter. Think about this, what that number means. Then 1 milliliter, if I take out 1 milliliter and measure it, it will weigh 1.48 grams, okay? Or vice versa. If I weigh out 1.48 grams of chloroform, it will have a volume of 1 milliliter, okay? That's its ratio, and we can utilize that. And remember, I can write it with grams in the numerator or grams in the denominator. Chloroform is the old chemical they used to use when you were put under for an operation to knock you out. Now, they don't use that anymore as far as I know. So any matter has a density, and we can write its density in 1 or 2 ways, with grams in the numerator or grams in the denominator. Depending on the question we're asking, the units we're searching for. And this is where we were setting up the problems with units so we can set it up properly to find it. Okay, a real straightforward density question. So what is the density of a necklace? If it weighs 484.56 grams and has a volume of 25.64 milliliters. Okay, so straightforward. There's our ratio. We plug in the numbers, 484.56 grams, 25.64 milliliters, keeping track of our sig figs. The denominator has 4 sig figs, the numerator has 5. So our answer should have no more than 4 sig figs. Okay. Our units, don't forget our units, grams or milliliters, they don't cancel out, they carry through, okay? So that necklace has a density of 18.90 grams per milliliter. Grams per milliliter. All right. Now, using density in the calculations. Well, here's the problem we're given. Chloroform, the same chemical, has a density of 1.48 grams a milliliter. The question ask, how many grams would 17.5 milliliters of chloroform mass? If I were to measure out 17.5 milliliters of chloroform, how much does it weigh? Now we can measure that out and go to the balance, but we don't need to do that because we know the density, so we can actually use the density to determine the mass of that body. Okay, so we set up the problem given we're 17.54 milliliters. We set up the conversion factor, which is the density, with grams in the numerator. Okay, why? Because that is what we're looking for. Milliliters cancel. The question asks for units of grams, so we set this up in this manner. Now, the periodic table has a number. All the elements in the periodic table have a small decimal number in there as you get a chance to look at it. And it has a number. For example, under carbon, there's a number that says 12.01. Okay, no units are there. But every element has a units of grams per mole. Right now, we haven't talked about moles, but those are the units, grams per mole. And we're going to use those conversion factors. We're going to use that atomic weight to do conversion, convert to other factors, to other units. Here's another ratio, grams per milliliter. Okay, I set this problem up with grams in the numerator because that is what the question asks. I can easily change that ratio to those units of grams per mole. All right. So again, don't keep in track of your sig figs. Remember, 1.48 is a measurement. The density is a measurement. You can remember it's mass over volume. Those two things are measurements. So yes, they will be a factor with respect to sig figs. They're not exact. And so we got 3 sig figs. Our answer would be 25.9 grams. It is not 25.9 grams per milliliter. Why? Because milliliter units cancel. Okay, remember that. You see a lot of answers when the question says how many grams, they're asking you, well, how many grams? And you're only going to have 1 unit, not 2 units, grams per milliliter. All right, so here they're asking the question, how many milliliters? Okay, so we're looking for volume. If we're given 0.0735 grams of chloroform, same material, if we're given that amount, that number of grams, what is its volume is what the question is asking. And so therefore, again, we write down what we're given, 0.0735 grams. We use the density of chloroform again, but this time we write it with milliliters in the numerator. Why? Because those are the units that we are searching for. And I check my other units and make sure they cancel out, okay? And if I inadvertently wrote it with grams in the numerator, look at my units. I get grams squared per milliliter. Those units don't make sense, okay? So that's an indication you set up that ratio incorrectly. And so that ratio set up properly. And now it's a matter of just doing the math, keeping track of your sig figs. There's 3 sig figs involved in both the density and the number given. So our answer should have no more than 3 sig figs. Okay. All right. Good. All right. So those are examples of using density. But keep in mind, you can use the same system if you have any ratio. Okay. You know, let's say, for example, and you might think, well, how's that? Well, let's make it a real life scenario. All right, let's say you are making $150 per hour. Okay. And the question is, how many hours needed to make, I don't know, $1,000? Okay. So how many hours are needed to make $1,000? How would I set that problem up? With the same method that we just been talking. Okay, 7.6, 6.67. Okay, well, how would I set that up? How could I write it out where it's set up to show the work? Those numbers look reasonable. Okay. 1,000 over 150. Okay. Well, all right. So we want 1,000. Okay. Our conversion factor is hours, right? So 1 hour is in the numerator divided by 150. Would that be correct? Do my units, my dollar units cancel? Leaving me with hours. Okay. Right. Now, Kathleen, you wrote it 1,000 over divided by 150, which is correct. But if I wanted to show work and conversion factors, and then I had a bunch of chemical reactions, I would have to set that up. Okay. What if, how many minutes needed to make $1,000? Wouldn't I need one more conversion factor here? Would I not? Because I know there's 60 minutes per 1 hour. Would that be correct, the way I set that up? I'm given $1,000 is the number. My factor, my rate is 150 per hour. So I write 1 hour in the numerator, 150 in the denominator. That gives me units of hours. Now I want to convert that to minutes. I know there's 60 minutes in the hour. My units all cancel out. Okay. My units of hours cancel right there. I mean, I don't have, so I can't write them in the true ratio, but if you write that out by hand, you can see how the units cancel. And I set up minutes, okay? And what if I wanted to change that and say, okay, well, how many seconds do I need to work to make $1,000? Well, what do I need another factor here, right? Because I know that there are 60 seconds in 1 minute. And now, with my conversion factors and keeping track of my units, I'm able to calculate how many seconds needed to make $1,000 if I work at a rate of 150 per hour, okay? That number looks reasonable. Caffeine, I didn't plug it in, but I just set that up off the top of my head here. But yeah, 60 times 60 divided by multiply by 1,000 and divide by 150. That looks reasonable. So 24,000 seconds. Okay, 24,000 seconds. All right. So the point of all this little quick exercise was to set up your conversion factors. So you got them all lined up so you can start canceling your units. Yes, I know I can take the 1,000 divided by 150, but if I got to take that out further, especially when we start talking about chemical reactions, I can't overemphasize that. We're going to get into chemical reactions, and by getting in the habit of setting it up with the conversion factors, we will be able to do calculations. For example, okay, you might see something like 2 A's plus 3 B's gives me, I don't know, 4 D's, okay? Those numbers are coefficients. It's kind of foreign right now, but those are ratios. There's a ratio of 2A over 3B or 3B over 2A. There's a ratio of 2A over 4D. We're going to be using those ratios to do these calculations, okay? These type of calculations. It will make more sense when we get to it, obviously, but I can't overemphasize setting them up in this manner where there are factors there and keeping track of union. Okay, so that's good. Let's finish this up. We're almost done here. And we take a little break. Anyway, temperature. Temperature and energy, okay? They're not related. I mean, directly. Energy has an effect on temperature, and temperature is what we do, is a measurement. We measure the temperature, obviously, with a thermometer, okay? And we know that when molecules are warm or hot, that they move much faster, okay? I mean, think about it. You're on the beach, you're on the beach, hot 100 degrees outside, you're walking in, you got to go from point A to point B in the beach. You're not going to stroll gently, right? You're barefooted. It's hot. The sand's hot. You're going to go a little fast, okay? Because it's warm. So hot molecules move fast because they have high energy. Now, the thing about energy, Mother Nature does this. Mother Nature doesn't like being in the high energy level, okay? And what we call an excited state. It will absorb energy, but once it absorbs energy from where it was, what is called the stable state, it will have to release that energy. It will release the energy to get back down to where it is comfortable, if you will, okay? So energy travels from a high level to a low level. Now, we can make it go the other direction, but to make it go the other direction, we got to put energy into the system. So spontaneously, energy goes from high to low. Cold molecules, they tend to move slower, okay? That's why we have condensation on the outside container of a cold container, because the water molecules on the outside have high energy, and when they touch that cold surface of your container, they lose that energy because they have high energy, and they condense and they move slower, and they condense and they change their state, go into liquid, okay? Because they have low energy. Now, thermometer, we use that to measure temperature. Now, there's 3 scales we work with. Everybody's familiar with the Fahrenheit scale. That's the English units. But in science, we use the metric scale, which is centigrade, letter capital C. There's a third one that we use in science called Kelvin, letter K, named after Lord Kelvin, by the way. Now, Fahrenheit and centigrade, they have infinite values. They can go in the positive direction to infinity, and they can go to the negative direction to infinity. Kelvin does not. Kelvin stops at 0, down at at negative at 0 Kelvin, we call that absolute zero, okay? Which means that matter is supposed to stop. All matter moves, no matter how cold it is. Even when it's freezing, the molecules are moving. What's supposed to happen, absolute zero, even that movement is supposed to stop. We haven't verified that because we haven't gotten that close yet. We got close, but not close enough. So anyway, the relationship of temperature is this. For example, boiling of water. At centigrade, it's 100 degrees, which corresponds to 212 in Fahrenheit. Freezing of water is 0 degrees, which corresponds to 32 degrees in Fahrenheit. Now, the relationship between centigrade and Kelvin is simply this. You take the Kelvin temperature and add 273. So at 100 degrees, boiling point of water, that corresponds to 373 in Kelvin. At 0 degrees freezing point, that corresponds to 273 Kelvin. Okay. Now, if we start with Fahrenheit and we need to get to Kelvin, we need to first convert from Fahrenheit to Celsius, then we can get to Kelvin, and vice versa. So you cannot get to Kelvin unless you go through Celsius. All right, and the relationship is as follows. Now, you don't have to memorize these calculations. Why? Because in the shapes table, which is one of the tables that you need to print and use because we make a lot of reference to it, the calculations for temperature conversion is given to you, okay? There. And so simply, if you had the temperature in Fahrenheit, you want to get to Celsius, you simply take Fahrenheit, subtract 32, and divide that value by 1.2. If you are in Celsius and you want to move to Fahrenheit, you take Celsius, multiply that by 1.8, and add 32. That gives you Fahrenheit. And Kelvin is simply adding 273. Okay. So try this with this example here that Phoenix can get up to 115. Your number, you should get 46 Celsius, and that corresponds to 319 Kelvin. Okay, so try that, see if you get the same numbers. Now, with respect to energy, okay, the question says here, which of these two beakers has a higher temperature? That's kind of a silly question, really, because when you look at that, you see 100 degrees on both sides, all right? And so they're both the same temperature. But the next question you might have to think about for a second. It says, which has a greater amount of heat, A or B? Okay, a greater amount of heat. And what do we got here? B? Okay, well, let me ask you, heat / energy. Let me ask you this question. I got an A and I got a B. Okay, well, this will answer it for you. I got two pots of water. One small little pot of water that maybe has got a few cups of water is boiling on the kitchen tabletop. The other big pot, I'm going to make spaghetti. Okay, so I got both of them boiling. They're both boiling 100 degrees Celsius. It's water. It's going to boil same temperature. Now, I'm given the choice. Which one do I want spilled on me? That little pot of water or that big spaghetti pot? Well, which one would you pick? I would pick the little pot if I had the choice. Okay, why? Because there's less atoms in there. Less atoms, though they're boiling 100 degrees like the big pot. There's less energy in the small pot. So the damage is going to be painful, but it wouldn't be as painful as that big old giant pot of spaghetti water coming at you. Because there's more molecules. There's more molecules in that big old pot. And this quite drastic, because I don't know if you ever heard of, with respect to weather, the term El Niño and La Niña, okay? Other than little boy and little girl, does anybody ever heard what is that El Niño? Anybody have any idea? With respect to weather? not a hurricane. Not a hurricane. It will cause hurricanes and problems with the weather. But what it is it's a body of water out in the Pacific, extremely large body of water that has a temperature differential. I believe it's a little bit higher than the rest of the ocean, a couple of degrees. But because it's so massive, it really has a big effect on the world weather. Now, El Nino is the big, massive chunk of water out there, and La Nina is just a smaller mass of water. Also has an effect on the weather. So yeah, it has a lot of energy in there that has a massive effect on the weather. Yeah, the temperature out there in the ocean is not consistent. You ever been in a river where it could be in a swimming pool and there's like a bit, especially in the river, you're wading in there and all of a sudden you feel this cold stream coming by. It's because that there's a gradient in temperature in water. It's not consistent. Okay, so with that, heat transfer, always high to low. And so if we're making cookies, okay, take the cookies out. Who's losing heat? Obviously the cookie, right? And who's gaining heat? Your hand. It gets hot because it's transferring the heat. Remember, the cookie has high energy. You grab that cookie, you're transferring that energy to your hand because it has a lower energy. And it transfers quite a bit, and it burns. Be careful. With respect to this example here, where they're taking a piece of metal, put it in the freezer, and then they put in a bucket of hot water. Eventually, the temperature of the metal increases because it gains the heat. Makes sense, right? Because it's in the freezer, it's at 0 degrees, and then you dump it in the boiling water. Why it goes from 0 to whatever temperature the boiling water is 100. It goes up. Eventually, both of them, all of them, go back to some temperature that is equal to the environment. So if you make a cup of coffee, nice hot cup of coffee, and you come back and you leave it in your tabletop, and you come back, it's not going to stay hot, right? It gets temperature, it loses its energy, and it equates with the temperature of the environment, okay? And whatever the environment is in your home. So you're going to lose energy. All right, so much for this part. So exam obviously coming soon, that quiz, and practice your conversion factors and density, maybe some temperature problems. Get well versed with sig figs. Sig significant figures are used throughout the semester, okay? In science, we're always aware of our values with respect to what we report, and we'll be doing calculations throughout the semester. So sig figs do our factor throughout the semester. If you got homework due, don't forget to get it completed and so forth. All right. Congratulations, you're done with chapter 3. Let's take a short 10-minute break, okay? Okay, the question is the problem with the lockdown browser assignment. Okay. Here's a question. How many people are having issues with the lockdown browser? Now, before you answer that question, the lockdown browser is only for the exam, okay? Does not pertain to the lab, does not pertain to the other assignments, only for exams. Now, what it is, let me explain what it does, is it's an app that's downloaded to your computer or your iPad, so that when you have to take an exam, you click on that app, and it is made specific for the Maricopa schools. So from there, you log in to Canvas like you normally would, okay? And then you go to the exam that requires the lockdown, and you do the exam like you normally do. What it does is the browser gets locked, so you can't go to other sites. Okay. Now, there has been some issues, and I don't know, the Chrome, some of you have a Chromebook. I did find out that it does work with the Chrome. And then there's a couple of people who had issues with the Mac. Now, is there anybody out there using a Mac that has downloaded the app and seems to be working okay? You can unmute yourself if you like and tell us about it. Okay, Kathleen, your Mac works fine. Did you have, when you downloaded it, it downloaded a zip file and then you had to extract it, correct? Okay, you extracted the file and then you did an installation, and then I'm assuming it created an icon for the lockdown browser for the Mac. Is that a correct statement? Yes. Okay. And then from there you can click on that browser when you need to do the exam. Okay. So you don't need that lockdown for anything else. You just need it for the exam. That's it. Now, is there anyone else? How about the PC people? Everything worked fine with the PC people. It won't work on your mobile phone, so you can't use it on a mobile phone. It works on a Mac, PC, any iPad people? Okay, Sarah is not working on your Mac. Could you can unmute yourself, Sarah, and tell us what we take a few minutes here because this is important that we make sure everybody's got the lockdown working. So we got Hannah and Sarah.
Hi, so I just can you hear me?
Yeah, good.
Okay. So I just downloaded it, but when I click on it, it's nothing just open. It just freezes, and again, it's going back to the first link. It's nothing open.
Okay, let me see. Who else said that theirs is working fine? Mine is Hannah, also the same way, Hannah?
Yeah, mine is opening. As soon as I click on the icon, it redirects me back to the installation page. So I'm still like, the app is downloading, but as soon as I open it, it's wanting me to re-download it again and again and again. Okay. Now, Christina, how about yours? You says that yours work okay?
Yeah, mine's working fine.
Could you explain what you did for the Mac people?
I just downloaded it and then I dragged the icon down to the bottom of my screen. So it's just one of the icons that I can open something, and I just open it, and it won't let you open it if you have any other applications running. So it said like, please close all applications before like using, and then it seems to be working fine. Okay.
Yeah, that's true. It does. If you have anything open, else open, it will ask you to close everything before you proceed. And so let me find out. So it's Hannah and Sarah. Those two Macs are not working, correct? Yeah. Okay. Kathleen has a suggestion of updating your Chrome. That might be an issue. You might want to try that. I did send an email to IT and not heard from them, but I will definitely call them directly today when we're done and see if I can get some more tech support. Okay. But like I said, the way it should work, I don't know. Those of you that downloaded it and it just goes back, have you tried just erasing that zip file and then try downloading it again?
I've deleted it like probably 5 times now, and I did a hard restart on my computer. So
okay, let me make note of that. Is there a difference? One last question. Hannah versus Christina. Both of you are Macs. Now, I'm not a Mac person. I don't know. I'm a Windows person. But is there a difference between you two with respect to the Mac you're using as far as the operating system? Christina, what kind of operating system are you using on your Mac?
Chrome, I don't know. I have a MacBook Pro.
MacBook
So,
Pro? Okay.
yeah, so I don't know. Hang on, if I click on, I have Mac OS Big Sur version 11.2.
1.2. And Hannah, how does that differ from yours?
I have a MacBook Air.
Air?
and-
Okay.
Yeah.
All right. MacBook. All right. So that could be the difference. I'm not sure, but I'll find out.
Okay.
All right. Okay. So let me find out about the I'm assuming everybody on the PC is doing okay, no problem there. So it's probably just a Mac thing. All right, so I have 2:30. Okay. I have 2:30. Let's come back about 2:35, and then we'll continue with chapter 4, unless there's some questions that you want to go over. Okay. All right, I'll be right back. Make it 2:40. Be right back. Okay, I'm back. All right. Well, chapter 4, there is not any questions. I'm going to jump into chapter 4. This one, we're going to get back into chemistry. This first chapters, we're dealing with calculations and so forth, but we're going to get back into the chemistry. Specifically, we're going to be talking about, first of all, no questions, right? Any questions? If you do, shoot me an email. Also, too, like I stated, drop in my other classes. Feel free to do that, okay? All right, chapter 4, having to do with atoms. Now, a lot of our work or model that we have really got started way back in 1800s. And then proceeded into 1900s, and since then has been progressed and improved and adjusted, and like any model that we have. But it started back with 1800s with a scientist by the name of Dalton, and he had his atomic theory. He stated that an element is composed of made up of tiny indestructible particles that are called atoms. Well, the term atoms was not nothing new. It's really a term that was used even as far back with the Greeks. But he wasn't 100% here correct with respect to them being indestructible, because it turns out that these atoms are made up of even smaller particles. And these are the ones that we're going to talk about eventually. And that's specifically the proton, the neutron, and the electron. Okay. So he also proposed that an atom was an element with all with identical and had the same properties. They were all identical and had the same properties. Well, that also really wasn't quite true also, as it turns out, because it looks like, for example, diamond, which is made up of, a pure diamond is made up of carbon, okay? A carbon, ordinary carbon, element number 6. But we also can make things like dry lubricants that contain carbon. And here we are, carbon being either in the form of a diamond or in the form of a dry lubricant. It's still carbon, same number of, same element, but totally different. Diamond is the hardest thing on earth, okay? Whereas the dry lubricants, that's what its function is, a dry lubricant. And it turns out that it's the manner in which the atoms are put together relative to each other that gives the properties. And even a slight change drastically changes the properties. Like I said, diamond in this dry lubricant. He proposed also the following, in that all the different elements combine to form compounds. And this is true. We still define a compound is a material that is formed from 2 different elements, at the minimum 2 different elements. So here we have a diagram of, say, 2 diatomic elements. Who knows what they are? Could be anything. Forming a compound. And you can see we got the golden green sphere combined with the red one. Totally different compounds. It's a typical chemical reaction. Now, also along Dalton's theory is that when compounds come together, they come together in whole numbers. They don't come together with half atoms, 3/4 atoms, or any other percentage or ratio. It is whole atoms. For example, the formula H2O, which is the formula for water, means that we have 2 atoms of hydrogen combined with 1 atom of oxygen. Okay. And that's what the subscript is. Subscripts are always being whole numbers. Now, once we put these together and we set the subscripts, those are etched in stone. You have a question about H20? Thomas, what's H20? Oh, H2O, sorry. Okay, what was your question? You can go and unmute yourself if you like.
Yeah, so if oxygen and hydrogen are both like flammable on their own, how come water isn't?
Well, when they combine together, the way they're put together is that oxygen's in the center and you got hydrogen now, not as an element, but a part of a compound. So it's no longer hydrogen by itself, diatomic hydrogen. It is hydrogen combined with another molecule, totally different. And so it's totally different properties. And one of the properties of water is that it's not flammable. Okay, because it's not hydrogen by itself. Oxygen by itself, totally different. Two totally different components. Does that make sense to you?
Yeah, thank you.
Yeah, okay, no problem. Now you can take the water and hit it with some, put energy into it and break it apart back to hydrogen and back to oxygen, which those guys obviously are flammable. And that's why it's so important we find water out in space, because we can create oxygen and create hydrogen as fuel. All right, so they come together as whole numbers, not as ratios. Now, they also can form, when they come together, they can also form different compounds. And an example here would be what we call carbon monoxide, uppercase C, uppercase O, oxygen. They come together to form carbon monoxide, the models on the left there, or they can form carbon dioxide. Notice the naming here. One oxygen, we call it carbon monoxide. Two oxygens, we call it carbon dioxide. Now, again, in this example, we have a bond between a carbon and an oxygen. Totally different properties than, let's say, a bond between two oxygens. So it's a totally different material. Now, generally what also when they come together, there is one element that is the central element, okay, the central atom. In the case of carbon monoxide, there really isn't. It's just two, it's linear, you know, they're kind of together and that's it. But when we start adding more other elements to a compound, there's always one that's a central atom, of which we would tell you which one it is. So in the example of carbon dioxide, the red sphere represents the carbon, and notice the gray one represents the oxygen, and they're bonded in a specific manner. We're going to learn how these things are bonded. But here, the carbon is the central atom. Normally, you'll see it underlined or maybe put in bold, and that signifies it as the central atom, and everything else is bonded around that. Now, so here we go. We're getting close to the 1900s, and so toward the end of the 1800s, we have a scientist. We call him good old J.J. Thomson. Now, he is credited with the discovery of the electron, okay? And as far back as 1897. And what he did, basically, he was able to create these particles. Didn't quite understand what they are, but, and I'm going to show you a video of that here in a second, kind of explain what he did. But he created these particles that hit this screen that contained this phosphorescence material. So here we go again with energy. So these particles have high energy. They hit the screen. They transfer the energy to the material of the screen. Those molecules, atoms, get excited. They're not going to hang out there very long because they're in an excited state. And so they come back to the ground state, but they have to give up that energy they absorb, same amount of energy, conservation of energy, and they give it up as light. So he would see a fluorescence on the screen. He is the precursor, J.J. Thomson. He is his equipment is the precursor to the modern the old television we have, the old big old giant heavy television. Because once he used this to demonstrate one of the subatomic particles, engineers got a hold of it and said, "Hey, we're going to make a television." So let's go over the video concerning this, and I'll stop it in between some of the comments. Notice there he's making these particles get shot out and they hit the screen here on the far right. They transfer their energy onto the material on the screen and the screen glows. So you can imagine if you ever see, maybe your grandparents had one of these old-fashioned televisions where you're watching this big old screen. This is the precursor of that. All right. Now, any charged material that travels from point A to point B has with it a component, which is a magnetic component. That's everything. That's current. Any current going through wires or just going through into space has with it a magnetic component. And so this is how he determined that this particle that is being shot out from the tube, from the cathode ray material, is deflected by putting a potential across there, plus and a negative potential. Notice that it got attracted toward the plus side. Negative and positive attract. And so that red beam particle must be negative charged because it's attracted to the positive plate, okay? And this is, again, the precursor from the old-fashioned television, because in the back of the television, that's why they were so heavy, it had 4 magnets. And they were able to control the magnets so you can control the beam as it scanned on the fluorescent screen so you can sit up front and watch your cartoons, all right? So here we go. And again, a moving charge particle has with it a component that is magnetic. Now, let me demonstrate that even more so. Let me change my background. This is, if you see my new background, if you look at it, it's basically just let me get my big head out of the way there. It is just a power source, copper wire magnets, okay? So there's electrons going through that magnetic moment. These little motor was put together by my physical therapy students at Carrington College. So we had an experiment to create a motor. And so as the current goes through the cable, that has with it a magnetic moment, a magnetic component, which is attracted by the yellow magnet. And then as it's attracted, momentum carries it over, so it starts flipping over. So this is an electric motor. Now we can do the reverse and actually create a generator. Generator works the same way, but it's in the opposite direction, okay? So now, you won't be responsible for this equation, obviously. This is way beyond the scope of Chem 130. But the point what he did here was he was able to calculate a value for that ratio of E over M. And you'll see in a few minutes, you'll see what that number is. And with that information, someone else was able to calculate E, okay? And from that, you can solve for M, which is the mass, which then you're able to calculate the mass of the electron. And so obviously here's a way to calculate the mass of the electron, because obviously you can't weigh that thing, it's so tiny. It's so tiny as far as the mass of the electron. In fact, the mass of the electron is so small, we're going to learn here about this more in a minute. We basically say its mass is 0. Okay. All right, so based on his information at that point, 1904, good old JJ came up with his model of the atom. And he proposed that someplace, somewhere, there is a positive part to it, okay? And that these electrons are kind of distributed throughout the atom by some means. Now, specifically, but by some means. So that came up with the what's called the plum pudding model, okay? Well, here we go. Now, here we go, 1900s. There's a lot of stuff going on in the science. You know, this is the time period of Einstein. We're all familiar with Einstein, but there was other scientists just as bright as Einstein coming up with models of the atom and so forth. Anyway, here comes another scientist by the name of Rutherford. Again, 1911, we're going 1904, and a few years later, 7 years later, we got his work. Now, he is credited with discovering the nucleus / proton, okay? Now, he did what we call alpha scattering. That part's not important, but he created some particles that he shot through a gold foil, okay? And this gold foil, these particles will go through the gold foil, and then they also would then hit a fluorescence material. And as they hit the material, they will also light up like JJ's experiment. But he found something astonishing. The plum pudding predicted that as I shot those particles, which are pretty big particles, everything could go right through. But what he was finding is some of these particles were ricocheting. They were hitting something in the gold particle that caused them to ricochet. Just like shooting pool, you want to shoot that corner pocket, you get that ball, get the ball go to the corner at an angle. Even some of them even shot straight back to the source. That was fascinating in itself that he observed that. So let's talk about, let's see his video here. Hopefully you can see, I can't see here, but you see them being scattered. You get spots like over here and back in the back. So they anticipated all of these coming up to the front here, but that wasn't the case. Yeah, exactly, Kathleen. A lot of the newer elements that we have been discovered have been named after a lot of these scientists. All right, so that proposed, Rutherford came up with a different type of model now. Based on his information, like I said, those particles were being ricocheted, which meant there must be something in these atoms that are pretty dense. And so he proposed that the atom must consist of a nucleus, okay? And so we have the nucleus where the bulk of the materials at, and the electrons are somewhere, still at this point, somewhere around it. We will learn with time that because of other information, that these electrons actually exist in specific energy levels, okay? And we're gonna learn that when we talk about that. So right now, we got a nucleus in the center, which is a proton. And then about 1932, Chadwick, he discovered the neutron, okay? And so what the model we have now is that in the nucleus, we have the proton and we have the neutron all in the center. And with the electrons around the nucleus. analogous to the solar system right now. But we'll learn that's a little more complicated than that. Okay, but we have been able to determine through indirect calculations that the atom is really a lot of empty space, okay? A lot of empty space. And if we were to kind of put everything in perspective, if the nucleus was, say, let's say the size of a small marble, and then the diameter of the atom would be roughly the size of the Cardinal Stadium. Another analogy would be if I were the hydrogen atom, I was the nucleus of the hydrogen atom, my electron would be roughly, I don't know, about 3/4 of a mile away. That's mind-boggling to me that here this material is so far away, but yet it's still holding on to the nucleus. Then what's even more fascinating from my perspective is we got the negative charge of the nucleus, and then we got the positive charge of the proton. And then, but they're not coming in and crashing with each other. Okay, they're still maintaining their distance. And there's a lot of power in there, humongous a lot of power. Note the hydrogen bomb, the atomic bomb, quite a bit of power in that atom. All right, so the subatomic particles that we're going to talk about are the electron, the proton, and the neutron, okay? Yes, these guys are made up of even smaller particles, and but that's beyond the scope here. Yeah, the electron has a symbol of E with a superscript negative because it has negative charge. The proton, lowercase p with superscript positive. And the neutron is neutral, okay? Its location for both the proton and neutron is inside the nucleus, and then the electrons on the outside. Here's the corresponding charge in each one, -1 for the electron, +1 for the proton, and 0 for the neutron. Their relative mass, what does that mean? Well, the masses are extremely tiny. So trying to work with these extremely small numbers can be challenging. So what has been given is what are called relative numbers or atomic mass units. If, for example, I'm at 200 pounds and someone else is at 400 pounds, well, I'm set at 1 and that person is set up at 2 because he's twice my weight. So we have a relative weight. He's got 2, I got 1. And that's what this means, relative weight. So proton and the neutron each have a relative weight of 1. And the electron essentially is being given a relative weight of 0 because it is so tiny. In fact, if the proton and electron weighed about 1,836 pounds, the electron would be about 1. So the relative weight is very small. So we treat it as essentially 0, bearing in mind that it does have mass. But it's so small that we will learn that the electron actually behaves like a light wave because it's so tiny, even with some mass. Okay, so with that information, we're going to talk now about the elements themselves and how do we write the elements. So obviously, there's 118 elements out there. No, we're not expecting you to memorize all of the elements there at all. But we do have what's called atomic notation, in which we represent the mass number, the atomic number, and their symbol. The SY is the symbol. And if you had a chance to look at the periodic table, you'll see that a lot of them have one letter, one capitalized letters, and a lot of them have 2, where you have a capital first letter and a lowercase second letter. So that is the symbol, okay? The mass number is a whole number. Okay? All these numbers are whole at this point. And the atomic number is also a whole number. And we write them out in the notation format in which is superscript left for the mass number, subscript left for the atomic number. And here's the thing. The atomic number is equal to the number of protons and the number of electrons. So if you pick any element on that periodic table, element number 32, whatever that may be, number 32 has 32 protons 32 electrons, okay? Now, keep this in mind too. If I have 32 positive charges and 32 negative charges, what is my net charge? Okay. Neutral or zero. Keep that in mind, because all the elements have a neutral or zero net charge because they equal number of protons and equal number of electrons. We're going to be learning that the metals, may I mention it, but all metals want to lose electrons. And when you lose electrons, you become positive, okay? It's just like, I guess you can use in psychological terms, if you lose negativity, you have a more positive attitude, right? And the converse is true. If you gain negativity, you become a negative attitude. This is true. All the non-metals tend to gain electrons and they have a net negative charge. All the metals tend to lose electrons and they form a net positive charge. What's happening there, by losing and gaining electrons, you form what are called ions, and those are, you may know them as electrolytes. So when you're chewing on, you say you need iron for your diet, for example, you're not chewing an iron metal, you're chewing on ions, okay? You're ingesting the ions because your body cannot deal with the metal itself, the element itself. It deals with the electrons, the electrolytes. But more on that later on. Now the mass number, remember, the protons and the neutrons have whole numbers. They're atomic mass units. And so the mass number is the sum of the number of protons and the sum of the number of neutrons. Now, let me get a better picture on this for you. Let me call up, where'd it go? Okay, I'm going to share the website. My dog here is crying, trying to go on. Okay, under modules of the course website, I have a module set up with additional resources. Okay, and there's a link there called labeled Build an Atom. If you click on that, it will initiate the simulation. Okay. And you can play with the game or the symbol, but I'm just going to click on atom. Now, on the atom, this pops up. I'm going to highlight a couple of things here for you. All right, we have three buckets here. We got protons, neutrons, and electrons. Now, notice what happens when I grab a proton and I bring it in. I created hydrogen. If I grab another proton, I created helium. And if I continue, I create the next element. The point is this. Now let me do this. Let's put a neutron. I created hydrogen, one proton, but I put a neutron in there. I still have hydrogen. I put another neutron. I still have hydrogen. Okay. I added an electron. Guess what? I still have hydrogen. I add a second electron. I still have hydrogen. Okay. The point is this: what defines an element is not the electron, not the neutron, but the proton. As I increase the number of protons, I create a new element. I can lose and gain neutrons and electrons all day. Yet, neutrons are extremely necessary because they're the ones, they're the ones that make the elements stable as much as possible, okay? So let's go back. Now, the other thing too is as I grab a neutron, and even if I bring it outside close to the inside dotted line, it goes to the center. Now, these dotted lines here, the circles, they represent energy levels. Right now, essentially, it just moves in order along the table by adding a proton. You're correct. So as I add, when I start with one proton, I create hydrogen, and I can just move all along. Okay, keep going, keep going, keep going. And I forget how many I can do here, but I'm going to stop at carbon. Okay, just so carbon. If you look at on your periodic table, carbon is element number 6. It's got 6 protons. And just what we learned, it also has 6 electrons. And notice when I stick electrons, they fill in the first dotted line circle. If I try to put a third one in there, it goes to the one outside. Okay, because we're going to learn that electrons actually occupy specific energy levels. Okay. Now, as far as stability, see how unstable it is? One of the functions of the neutrons is to give the element stability. So as I proceed, one more. Okay. How difficult would adding protons be in a lab? Oh, you mean actually try to do it in real life? In like an experiment where you're going to put a proton in there? Yeah, it would cause an explosion, a big explosion. It's called fission, and there's a lot of energy, and it'd be extremely dangerous. Extremely dangerous. So yeah, I wouldn't do it in the lab. Yeah, exactly. In fact, the other thing too, for if you go look up the periodic, if you look up where lead is on the periodic table and where gold is, in order for lead to become gold, somebody's got to lose protons and neutrons and protons, and they're inside the center of in the nucleus. And in order for that to happen, you gotta break that atom up, and that's going to be a lot of energy release. Yes, when they make new elements, in fact, they're working on number 19. The last 3 were made a couple years ago. I think it was 113, 115, 117, I believe. Basically, you're putting them to a particle accelerator, and you are taking these particles and you're forcing them to come together to create a new element. And it takes a lot of work and a lot of energy, and you got to be real safe. You got to be careful because you don't want an explosion. You know, putting things together, let me give you an idea. It's happening, okay, when we break an atom up, that's called fission. When you bring them together, that's called fusion, okay? In both cases, there's a lot of energy involved. The atomic bomb is an example of fission. The sun is an example of fusion. It is bringing hydrogen atoms together to make helium. And in the process, it's giving up a ton of energy, a ton of energy. You know, that's a good question. I don't know about the scenario with the accelerator, but they've already done quite a bit of work with it in Europe, specifically in Europe, and I've not heard of any problems at this point in time. Yeah. They are searching for, there's, the theory is there's one subatomic particle that makes up everything. You know, imagine having Lego, like if you have Legos all the same color, you know that you can get a Lego, and if you have a million of these, you can create an infinite number of designs and so forth. Well, it's thought that matter is the same way, that everything is made up of a particle, one particle, which creates the protons, creates the electrons, creates the neutrons, and from that, those guys, they make up the different elements. So They're searching for that particle right now. Anyway, so back to this. So this simulation gives you an idea how things work. And here's the mass number that I was talking about, which is the sum of the protons and the sum of the electrons. Now, we've all heard about carbon-14 dating, carbon, different types of dating. That's a means to measure how old things are. Now, the way that works is every element has what we call isotopes. And all isotopes are that they have an extra neutron. Okay, here's, for example, right now we're dealing with what's called carbon-12. That is the most abundant carbon in nature. But there is also carbon-11. Whoa, did I grab the right one? I gotta make sure I grab a neutron. There is carbon-11 in nature, meaning it's missing one neutron. Notice the mass number of carbon-11, okay? There's carbon-12, which is the most abundant isotope out in nature. But there's also carbon-13. And guess what? There's also carbon-14, which is not very stable, but it's there. Trace amounts, okay? The point of this is that isotopes are nothing more than that element that has one more or less neutrons. They're still carbon. It's just they have extra baggage by adding more neutrons, or they got less baggage. Now, as I stated, some of them are very abundant in nature, but they exist. Carbon-13, I believe is about, I have a number in one of the slides, a few percentage. Most of it is carbon-12, which is about 98, 99%. The point of this, there's 4 isotopes of carbon, whole numbers, 11, 12, 13, 14. All 4 of them have a certain percentage in nature, okay? Just like your grades consist of a percentage from the homework, a percentage from the exams, the labs, activities. Well, what happens is, knowing the percentage of each isotope, we actually get an average weight for all the isotopes. And that is why on the periodic table, if you look up under element number 6, which is carbon, you find a number there that is listed as 12.01, okay? And that is the average atomic weight of all the 4 isotopes of carbon, given the percent amount that they give to nature. So what that means is we can determine the most abundant isotope of any element by looking at the periodic table, and which I'm going to pull up here. And taking the atomic weight, which is underneath the symbol, and let's take carbon, okay, which is element number 6, 6 protons, 6 electrons, okay? Now we want to determine how many neutrons that is. Remember, the neutron, the mass number is the sum of the protons and the neutrons. Well, the mass number for this carbon, we can take the 12.01, round it up to the nearest whole number, because that is the most abundant carbon in nature. So that 12.01 would be 12, right? So take 12 and subtract the 6, and that gives you the number of neutrons for carbon-12. You can do that for any of these elements. For example, let's do what is the most abundant element for sodium. That's number 11. Let me say that again. What is the most abundant isotope for sodium? But to answer that, you go to the periodic table, look at the atomic weight, which is that number underneath the symbol, 22.99, round it up to the nearest whole number, and that is sodium 23. Take 23, subtract 11, you have 12, which means that's 12 neutrons. So sodium, this sodium has 11 protons, 11 electrons, 12 neutrons, and the most abundant isotope is sodium 23. Okay, and that's all from the periodic table. You don't have to memorize all that information. You just got to find it on the periodic table. If we take zinc, zinc is number 30. Okay, it has 30 protons, 30 electrons. Okay, the most abundant isotope of zinc is zinc 65. Okay, can anybody tell me how many neutrons does zinc 65 have? What's 65 minus 30? 35. You're correct. Now 25. Okay, 65 minus 30 is 35. Okay. All right. So again, using the periodic table, you can one or two things. Now, multiple things is one from the atomic number. Tell you how many. Where is the 0.3 N? Okay. Oh, that's what I was saying. Remember the example I said about carbon? Carbon 11, carbon 12, carbon 13, carbon 14. Each one has a percentage contribution to nature. Those whole numbers, 11, 12, 13, and 14 are average. You add those numbers up, divide by 4, you will get a decimal number. And that's what's happening. Zinc has multiple isotopes. Okay. And that 65.38 is the result of averaging those whole numbers. Okay. Take a number 2 and 3. What is the average of 2 and 3? 5 divided by 2, right? Which is what? 2.5. So the average of the whole numbers of 2 and 3 is 2.5 in the middle. But if there's like 90% more 3 and there's 10% more, 10% of 10, then that average will be skewed toward closer to 3. Okay. And so all the atomic weights, that's what these numbers are in the periodic table, are the atomic weights. The decimal numbers are the average of all the isotopes for that element. And that's why you have a decimal number. But because of the percent contribution, like I explained, the average between 2 and 3, and let's say you had more 3 than you had 2, like 90%. So the average will be skewed over to about maybe 2.8. Okay, because there's like 90% 3s and 10% 2s. So the average of that distribution will be about 2.8. So I can take the 2.8 and round it up to 3, and that will give me the most common number, which I said 90% is 3. Okay, does that make sense? That's why these numbers are decimal numbers. And that's why you can round the atomic weight to the nearest whole number. That's what I just explained, Thomas. What bottom number? Oh, the bottom row? Oh, sorry. And now we're going to explain that one too. Those guys with parentheses, the numbers with parentheses are extremely radioactive and not very stable. And so the point is they exist for a period of time, but there's not enough time to analyze all the isotopes that exist. They're not stable to break down to other parts. So because of that, they just throw in parentheses around it to signify that they are radioactive and they break down, and there's not sufficient data to show what's the average atomic weight, because they can't isolate the all the isotopes for a longer period of time. Yes, they do decay into other elements and particles and energy. All right, so where was I? All right, so we'll go back to this. Good questions. Oh, let me where we at. All right, so we got atomic number, which is lists the number of protons, number of electrons, and the mass number is the sum of the protons and the neutrons, which are whole numbers, okay? The mass number is not the same as the atomic weight. The atomic weight is a decimal number. The mass number, the number of protons, the number of electrons, and the number of neutrons are whole numbers, okay? All right. Excuse me. Every element, every atom of element has the same number of protons. You know that. And we know that the number of protons also corresponds to the number of electrons, which tells us that they are neutral. The number of protons defines the element, like I showed you in that simulation. By adding protons, you create a new element, totally different properties, okay? So the proton defines what the element is. The neutron just defines what type of isotope it is. And the electron, you lose or gain electrons, you still have the same element. It's just that now you're a charged particle. If you, not a particle, but a charged ion, a charged element. The sodium, for example, the sodium that you put on your French fries is not the same sodium you find on the element, on the periodic table. The periodic table is the element. It has 11 protons and 11 electrons. The sodium that you put in your French fries has lost 1 electron, and that's the ion. That is what you ingest, okay? Which is a good thing because the sodium on the element, on the periodic table, I don't want to ingest that because it's so reactive, it would cause a little bit of a problem in your mouth as soon as it touched liquid water. So carbon atoms always have 6 protons, regardless of what state, what form they're in. Carbon dioxide, that carbon has 6 atoms. The carbon in your fatty tissue, it's a fatty acid, that's carbon, 6 protons. The carbon that's utilized to burn your fuel to drive your vehicle, that carbon has 6 protons, the same carbon, okay? The carbon in the diamond, 6 protons. The carbons in the graphite, 6 protons, okay? They're just in different forms. Excuse me. We talked about atomic mass unit, it's relative. So the mass number is the sum of the proton, the sum of the neutrons, okay? Now, what we do is take that equation, rearrange it for neutrons. So it's a mass number minus number of protons. So for the most common abundant isotope, we can simply go to the periodic table and round up the atomic weight, as I explained, and then subtract the number of protons, and that gives us the number of neutrons. Or it could be given to you. For example, potassium 40. Well, the first question to ask oneself is potassium 40 the most abundant isotope? Well, let's go through the periodic table, find it. Go to the periodic table, we find potassium. Potassium is right there. Okay, number 19. Its atomic weight is 39.10. That means that the most abundant isotope is potassium 39. Okay, so in this example, they're talking about potassium 40. So the difference between potassium 39 and potassium 40 is simply 1 extra proton. Excuse me, neutron. All right, so how we write this is the mass number is given to you. There's nothing to look for or look up because it's there. It's hyphen 40. But you've got to look up the atomic number for potassium, and it's number 19. Get that from the periodic table. So the notation for this is a 40 upper script, superscript left, a 19 subscript left, and the symbol K. Okay. How many neutrons does it have? Well, we simply have to subtract the 2 numbers. And for this example, for potassium 40, the number of neutrons, no, you couldn't have an infinite number of neutrons because they would be extremely unstable. It wouldn't Even in that simulation, if I kept adding protons, that thing would be jiggling all over the place. Where are we at? Okay, so for potassium 40, it has 21 neutrons. Potassium 39 will simply have 20 neutrons. Okay. Write the atomic notation for bromine 81. Again, you can check to see, is this the most common element for bromine? Well, we could go to the periodic table. Very quickly look for bromine. Bromine's number 35, because you got to look up the atomic number anyway. Here's bromine, 39, 79.90. The most abundant isotope be bromine 80, right? All right, give me 1 second. I got to do something real quick. Give me 1 second. Something came up. Okay, I'm back. Sorry about that. All right, so here we're writing the atomic notation. We're almost done with this chapter, by the way. It's a fairly short chapter. And so we look up bromine, Br. The mass number is given to you. There's -81. But we have to look up the atomic number for bromine, and it's 35. We find that from the periodic table. To determine the number of neutrons here, we simply subtract 81, minus 35 gives us 46. So for bromine 46, it has 35 protons, 35 electrons, 46 neutrons, okay? If we were doing the most abundant isotope of bromine, that would have been bromine 80. Then it also would have 35 protons, 35 electrons, but only 45 neutrons. Okay? Remember, the neutrons create new isotopes. It's still the element. Now, in the case of isotopes, when I briefly talked about this earlier, it's not showing carbon 11, but carbon 12, carbon 13, carbon 14, all of them are carbon. So they have 6 protons. They differ in the number of neutrons. Carbon 12 has 6 neutrons. Carbon 13 has 7 neutrons. Carbon 14 has 8 neutrons. And if carbon 11 was here, carbon 11 would have 5 neutrons. Those are the 5 isotopes. All right, so for here, if we have a table and we want to fill it up, and most of the information is already there. We're looking at oxygen 16, oxygen 17, oxygen 18. Well, the mass number is given there, okay? It's given to you 16, 17, and 18. Now, they're all oxygen. All of them are oxygen, so the number of protons and the number of electrons is constant, okay? All of them have 8 protons because, again, if they had a different number of protons, then it would be a different element. Everybody here is an oxygen, okay? They all have 8 electrons. Where they differ is the number of neutrons. And notice number of protons plus the number of neutrons equals a mass number. So 8 plus 8 is 16, 8 plus 9 is 17, 8 plus 10 is 18. Okay. And excuse me. Now, if you were to take the average of these three numbers, 16, 17, and 18, and the percentage of all that, you're going to get a different number. Now, what's happened is they made oxygen kind of the relative number. So if you look up the periodic table of oxygen, you'll find there's a correction factor for all the elements. So oxygen has an atomic weight exactly at 16.00. All right, so let's see where we at. All right, so this is why, as asked earlier, why we have a decimal number with respect to atomic weight. And the carbon is used as an example. This is trace amount of carbon-11, specific amount, but it's a very small number. The bulk of carbon is 98.89% on nature. Carbon-13 about 11.1%, or excuse me, 1.11%, and a small percentage for carbon-14. Okay, taking into account of these numbers, 11, 12, 13, and 14, taking into account the percentage they bring in to nature, there's an average of, that number averages out to 12.01. And that is why we can use a periodic table, look at the atomic weight listed on the periodic table, round it up to the nearest whole number, and that gives you the most abundant isotope for that element. So 12.01 rounded up to 12 gives you carbon-12, which is the most abundant isotope for carbon. All right, so with that information, the question is asked, well, okay, which is more abundant, lithium-6 or lithium-7? Well, to answer that, we got to go to the periodic table. Good old-fashioned periodic table here. We got to find lithium. Lithium is number 3. Okay, the atomic weight for lithium is 6.94. Round that number to the nearest whole number, that gives you lithium-7. Okay, so lithium-7, lithium has 3 protons, 3 electrons. Its mass number is lithium-7. How many neutrons does this lithium-7 have? Right here. How many neutrons does this lithium have? Sure. Not 7. Okay. The lithium that I highlighted, okay, 3 protons, 3 electrons, right? Its mass number is lithium-7. With that information, how many neutrons does this lithium have? 6. What's 7 minus 3? 4. Okay. 4 and 3 equals 7. So 4 is number of neutrons, 3 is number of protons, and number of electrons for lithium-7, which is the most abundant isotope. Lithium-7. Okay, so going back to the question, the most abundant isotope is lithium-7 because we use the periodic table to determine which is the most abundant isotope. Chlorine-35 or chlorine-37? Well, you go back to the periodic table, look for chlorine. Okay, we'll find that on the far right. There's chlorine right here, number 17. Its atomic weight is 35.45. rounded up to the nearest whole number, which is 35, which tells you that the most abundant isotope is chlorine 35. Okay, chlorine 35. So we go back here. Circle chlorine 35. Okay. All right. So a lot of the elements quite radioactive. So we have around, I believe, about starting 92 forward, they're all basically radioactive, and they just break down. And so we put a parentheses around their mass number. We don't have a atomic weight to give them, okay, because they're radioactive. For example, number 96, curium, has 247 in parentheses. Obviously named after Madame Curie. Side note, anybody know where Madame Curie was originally from? France? No. Actually, Madame Curie was originally from Poland. She did marry her husband, Curie, I forget his first name, who was French. But the reason she went to France, but during that time period, women were not, can you imagine this? Women were not allowed to go to college and to get further education. And at that time period, France was the center of all science. So she went to France to get her doctorate. And she got her doctorate, married her husband, Madame Curie, got the Nobel Prize twice. And then her kids also got the Nobel Prize. So it's a pretty smart family. Anyway, she was a chemist. Yeah, she was the queen, STEM queen. She was a chemist. All right, so we have here chemical formulas. We got 2 more pages and we're almost done. Uh-oh, my little assistant just showed up. All right. Now, when chemical formulas, all they tell us is how many atoms are put together in the formula. So therefore, like for example, H2O, all it says we have hydrogen, 2 hydrogens and 1 oxygen. Doesn't say anything about how they're put together in the structure. We will learn that with time, okay? So if we take this example where we have C3H6O6, it could be any multiple compounds, but that's the general formula. 3 carbons, 6 hydrogens, and 3 oxygens. That means we have a total of 12 atoms, okay? We need to learn to do this because remember, each one of these elements has an atomic weight. And if we take the atomic weight of carbon, 12.01 multiplied by 3, that is the total weight for the contribution of carbon. The total weight from the hydrogens is 6.06. Total weight for oxygens is what, 16,348. All that adds up to the molar mass of that molecule. So we got to learn to find out how many atoms of each we have. So 3 carbons, 6 hydrogens, and 3 oxygens. Now, occasionally you see this in parentheses, and this could be a little bit perplexing, but I'm going to direct you to the infamous periodic table. And if you look at the periodic table and you go to the bottom left corner, there's a table there that says most common polyatomic ions. All right. What this is a listing of polyatomic ions. These are ions that are made up of many atoms, different atoms put together. But the point is they are units. We don't take them apart. They come together as NH4. That's the unit. And that's true for all the other ones. You might be familiar with OH, which is called the hydroxide. They all have their own specific name, and they all are, that's their structure. We don't change it. Whenever we need to show we need more than one, we put a parentheses, and we're almost done. So bear with me. All right. And so you see here, we got NH4 in parentheses with a subscript 2. That means there are 2 of those packages of NH4, which means there are 2 nitrogens and 8 hydrogens all together, 1 carbon and 3 oxygens, for a total of 14 atoms, okay? 14 atoms. And again, if looking at the atomic weights of each one and the number of each one, we can figure out a total weight, a total what we call molar mass for that molecule. This, by the way, is called ammonium carbonate. All right, one last slide and I think we're done. H3PO4, I understand you don't know what these are, but I'm sure we will with time. And if you drink a lot of soda pop like me, you drink a lot of H2PO4, otherwise known as phosphoric acid. It has 3 hydrogens, 1 phosphorus, and 4 oxygens. Okay, the next one, you got Ca, which is calcium, and then you have one of these polyatomic ions, OH in parentheses. There's 2 of them. And if you drink a lot of Tums, this is probably what you drink, ingesting. This is called calcium hydroxide. It has 1 calcium, 2 oxygens, and 2 hydrogens. And finally, the last one, this is called aluminum sulfate. Also, another thing in parentheses, we go back to the periodic table that we just talked about. Look at this. You get the SO4, okay? SO4. Now, they have a charge, and we're going to learn about those here with time. And that's called the sulfate. I make you aware of those because we're going to be using them quite a bit. Al, good old Al, is called aluminum. So this is called aluminum sulfate. So we got 2 aluminums. In the parentheses, there are 3 sulfurs. There are 4 times 3 oxygens, 12 oxygens, okay? So for the first one, phosphoric acid, we got a total of 8 atoms. Calcium hydroxide has 5 atoms. And then the last one, aluminum sulfate, has a total of 17 atoms. All right. Okay, well, get to learn how to count each one because we're going to be able to do something like this and also some other things. The law of definite composition, as we mentioned earlier, that when elements come together, they come in whole numbers. They also come together in ratios. For example, H2O, good old water, consists of 11.2% hydrogen and 88.8% oxygen. We're going to learn how to calculate that. It's very straightforward, okay? But the point here is that percentage is consistent no matter where you get the water from, whether you get it here on Earth or you go to Alpha Centauri and pick up the water there. If it is H2O water, it has that same composition. We utilize that quite a bit in chemistry, specifically organic chemistry. When we make new compounds, we go and look to see what percentage of carbon, hydrogen, and so forth, so we can come up with a structure. Okay. Now, with that being said, we are done. And my assistant, my future chemist here, wants to say hello to everybody because she's kind of like, "What's going on?" All right. So, thank you. She's my assistant. She's like, "What's going on here?" All right, guys. So we got done with chapter 4. Let me stop the recording.